Let's discuss naming chemical compounds and writing their formulas. And this will be a broad review of ionic, molecular, and polyatomic compounds. First, binary ionic compounds. They're made of two elements. They're made of ions, atoms that have become electrostatically charged by losing or gaining electrons. The cations, the positive ions, attract the anions, the negative ions, and form very stable, very hard to break chemical bonds, very high melting points. Sodium chloride, calcium oxide, aluminum fluoride, and potassium sulfide are some of these ionic binaries. Molecular compounds are formed by atoms that share electron pairs. When sodium reacts, it loses an electron, and when chlorine reacts to form the chloride ion, it gains an electron. But when hydrogen reacts, it does not lose its electron, because if it did, it would be a bare proton, a hydrogen nucleus. That's a very high energy thing that we don't see outside a particle accelerator. So hydrogen bonds to other atoms by sharing its single electron and, of course, sharing the electron of the other atoms. A covalent bond is a bond in which electrons are shared, and that's how the energy drops. The energy is going to be permitted to be low, and that, of course, is always the direction in which we are going, is towards a low energy. In general, ionic bonds are formed between atoms that are far from each other on the periodic table, whereas covalent bonds are formed between atoms that are closer together on the periodic table. Typically, these are nonmetals. For instance, carbon and hydrogen, carbon and oxygen, nitrogen and almost anything except very strong metals bond together covalently. Now, something Bohr and others noticed. It appeared that only outer shell electrons have anything to do with chemistry. For instance, lithium loses only one electron and then has two electrons. It's then as low energy as the helium atom is. Likewise, oxygen can gain two electrons or share two electrons, but it only does that with its 6 valence or outer shell electrons. The 2 core electrons inside in the first energy level never participate in chemical reactions. So we came up with something convenient called the octet rule, noticing that all but one noble gas have an outer shell of 8 electrons, that is S2P6 configuration, and that appears to make them very low energy stable. 2 atoms then share electrons in order to give both atoms that kind of stability. Now, hydrogen obviously can have only 2 electrons, a single pair, to share. It takes one of its own electrons and then an electron from the other element that it bonds with. So here's some examples. Water is a good example. It's made of hydrogen and oxygen. The hydrogen has 1 electron to share, and the oxygen has 6 outer shell electrons. So, since it needs 8 to form an octet, it shares with 2 hydrogens, 1, 2, each of them needing to make an electron pair. The molecule then has a negative end here with those 2 lone pairs and a positive end down here with its 2 hydrogens. The shape of these 4 electron pairs around any central atom are tetrahedral. And of course, a tetrahedron is the regular solid you get from 4 equilateral triangles. More examples. Methane here, CH4. Ammonia, also molecular, covalent bonds. Carbon dioxide, the linear molecule you see here. Ethanol, C2, H5, and then this OH or hydroxyl group. Organic compounds and biochemicals are almost always entirely composed of atoms that are bonded together covalently. For instance, this is oxyhemoglobin, hemoglobin with oxygen attached. But every chemical bond in this huge molecule between two atoms is just one, maybe two, occasionally three pairs of electrons being shared. So stop this video and mark each compound mostly ionic or mostly covalent, then turn it back on and check your answers. Now, compounds with more than one atom in an ion are called polyatomic ions. Asking the question, what's the single most reliable measure of a nation's economic output? The answer is the number of metric tons of sulfuric acid it produces each year. Sulfuric acid is a ternary, not a binary compound. It has hydrogen, sulfur, and oxygen in it. And this is a sulfuric acid plant. Now, the most important ions are made up of more than one atom. I have here, but you have to look at your handouts for more complete lists of polyatomic ions, which you should memorize. So the positive ions, well, there's really only one really important one, the ammonium ion. Negative ions, or anions, acetate, carbonate, nitrate, sulfate, and phosphate. These are the most critical of them. And then, of course, you should also memorize the ones on your handouts. Now let's talk about formulas. Formulas of polyatomic ions and salts. For instance, sodium nitrate. Always remember, the ion stays together. The nitrate, the nitrogen and oxygen, the nitrate stay together. In this case, the cation is sodium, Na+. The anion is nitrate, NO3 with a -1 charge. Sodium has a +1 charge. Nitrate has a -1 charge. That means that they balance. The compound is chemically neutral, so the ratio of sodium to nitrate must be 1:1. Formula then is NaNO3. No need to complicate it with adding any numbers. Each one appears just once. The formula mass is 23 sodium, 14 nitrogen, and 3 times 16, or 85 grams per mole. Let's look at ammonium sulfide. The cation, ammonium, NH4+, the anion, sulfide, S2-. You need 2 ammoniums to balance this -2 charge on the sulfide, so the ratio of ammonium to sulfur is 2:1. Now, when you write this, you have to say the whole ammonium ion is taken twice. So the formula is, in parentheses, NH4, then the subscript 2 outside it, and then 1 sulfur, ammonium sulfide. Formula mass, this is 18, so we multiply it by 2, and we add 32 for the sulfur, 68 grams per mole. Now, read these, write them down, and your practice quiz, turn off the video, and see what the formula and formula mass of these 6 compounds would be. Here are your answers. You can check them turning off the video. Now let's talk about bases. Very simple. Inorganic compounds containing the OH ion are bases. These react with acid, something you probably learned back in middle school. The OH negative ion is called the hydroxide ion. All metals form hydroxides in the usual way, positive bonded to negative ionically. So NaOH is sodium hydroxide, a substance that's been used for many, many years, for instance, to make soap. Calcium hydroxide, CaOH taken twice. Ammonium hydroxide, which many people just call ammonia, it's a cleaning solution, is NH4OH. remember please, never mix ammonia with chlorine bleach. That is a deadly combination. And let's now talk about acids. Acids are compounds containing the hydrogen ion. These react with bases and with active metals. For instance, HCl, HBr, HF, or HI are binary acids. And the gas, now, outside of water, is called hydrogen chloride, hydrogen bromide, hydrogen fluoride, hydrogen iodide. But in water solution, they form acids, and they're called hydrochloric acid, hydrobromic acid, hydrofluoric acid, hydroiodic acid. Ic acids are water solutions of hydrogen ide, something ide, so chloride, fluoride, and so forth. They start with hydro and they end with ic. So, what would be the name of H2S in water? It's not hydrogen sulfide in water, it's hydrosulfuric acid. Hydrosulfuric acid. So, let's name these three. Again, turn off the video, stop the video, and then you can check your answer. Here are your answers: hydroselenic, hydrofluoric, and hydroiodic. Now, if you normally name an acid, if you would if you didn't know it any better, if you name an acid hydrogen something 8, you will call it somethingic acid. Here's what we mean. This would ordinarily be called hydrogen nitrate. Well, we don't do that. We call it nitric acid because it's got that H in front. This is hydrogen sulfate. We're tempted to call it, but we don't. We call this sulfuric acid, sulfuric acid. This then would be phosphoric acid, and this H2CO3 would be called carbonic acid. And of course, that's what gives the bite to carbonated beverages. Now, and finally, just a reminder about multivalent metals. Many transition elements form compounds in more than one way, have more than one valence available. That's due to the complex electronic configurations of these metals. They have d electrons. So, iron can lose either 2 or 3 electrons. Fe2+ or Fe3+ can form, and that depends on the conditions. So there are 2 iron chlorides, FeCl2 and FeCl3. We call the first one iron 2 chloride and the second one iron 3 chloride. So the Roman numeral tells us the valence or combining capacity of the transition metal. Older literature, however, calls the lower valence ferrous and the higher valence ferric. Sometimes you still see that in literature. Now, flex your muscles with these 3. What would the names of these 2? Copper 2 nitrate and copper 1 nitrate, and these 2, ruthenium 1 chloride and ruthenium 2 chloride.